So let's talk about the errors in our electrolytic lab. So if you remember, we did electrolysis of copper chloride. So we had copper chloride aqueous, and it's CuCl2. Specifically, it's copper 2 chloride because we're dealing with the copper plus 2 ion, which means in our blue solution, and I know this is a black and white photo, but what we have here is copper plus 2, and also we have the chloride ions. And so what we did in this lab is we wanted to find an experimental value of the copper that would be deposited at the cathode. And I made you use a power source, which is this is the voltaic cell. And what we did is we saw that this was the red lead, okay, and this was the positive cathode. And this was the black lead, okay, and this is the black lead, I'll write black. And of course, this is the negative anode of the power source, the DC power source, or we can call the voltaic cell. We know electrolytic cells require power. So this is our voltaic cell. Okay. And what we did is you guys decided where you wanted or where the cathode would be. Remember, this electrolytic cell is non-spontaneous. It's not happening right now until we make it happen with this very spontaneous power source. So we're going to decide. So you could have connected this any one of two ways here. So I'm just going to do it this way and make the anode connect here, right here, and you could have decided the opposite. Now, if that's the anode that's negative, it's going to make this electrode negative. And of course, electrons always flow from the anode, where oxidation is occurring, to the cathode. And the cathode is negative, and you can think so because electrons are being pumped to it by the anode. And of course, the red lead, in my diagram, you could have chose the opposite, okay, connects to this electrode. These electrodes, by the way, are graphite, so they're carbon solid, and the reason why we're using graphite is that they're pretty much unreactive under these voltages. And so if you've seen diagrams with platinum used, people get confused, hey, the platinum's being plated. No, we're using very, very unreactive electrodes as the conductor, as the vehicle where the oxidation and reduction is occurring. Don't forget, electrodes are the place where redox is occurring, okay? We have too many easy systems where you think always that one of the electrodes is undergoing oxidizing or reducing, and that's not the case here. So we're using the graphite. Any case, the cathode is positive, and this makes this electrode positive. And if it's the cathode, well, this must be now the anode. And we know that electrons are pumped back to the battery. Think of the power source as spontaneously pumping electrons this way, and the cathode of the battery, where reduction is occurring, pulling the charge or pulling electrons back toward it. And so electrons always flow from anode to cathode, and we should have gotten something like that. Now, what's of course happening is the way that I drew it, I'm making a negatively charged cathode, which means my copper in solution is going to, the copper plus 2 is going to be forced to reduce and make pure solid copper. Metals that are elementally, or I should say electrically neutral, are usually solids. Of course, there's one exception, and that of course is mercury. But we're not going to be dealing with mercury here, obviously. Okay, so we have the plating. The aqueous ion is being forced, and of course the plating, or in this case the collection of the copper, the mossy copper, because we're in an aqueous environment, is going to be happening here. All right, and of course on the other electrode, we're going to have the chloride ion be attracted to this electrode because it is positive. It's positive because electrons are being drawn away from it. And so the chloride ion is going to oxidize at the anode, just like the copper +2 is reducing at the cathode. That's always the case. Red cat and ox. So the chloride ion is going to send off an electron, and it's going to become chlorine gas. Elemental chlorine, what do we know? Well, chlorine likes to bond with itself. It's diatomic. Make this a little bigger, so 1 electron plus chlorine 0, but it really bonds to itself, so there's going to be 2 electrons and 2 chloride ions. And that's what happens here, and we're going to make chlorine gas, and that's why this was done under a fume hood, okay? Any case, that is our electrolytic cell. Now, the discussion I'm having here today, obviously in this lab, we we ran the experiment, and we tried to keep the amperage at about 1, okay? So you guys dialed up this, you turn this on, you turned on your phone or whatever you used as a timer, and we ran this for about 10 minutes, and we tried to keep the amperage at 1. We wanted an average amperage. However, we know that that didn't always stay at 1, and it was interesting to see that when we started collecting more of the copper, okay, the amperage was starting to increase, and we had to dial it down. And that's, of course, because the copper is a better conductor of charge than the graphite. So that was kind of cool. As that was building up, the amperage was running a little high, and we had to turn that down. Any case, okay, my discussion here today is to realize that we, of course, did a hot filtration, washed off the mossy copper there, and we measured out our dry filter paper and basically ran that precipitator, this solid copper, through our filter paper, dried the filter paper in copper, subtracted out the filter paper from that mass of copper, and we have our experimental mass of copper. And through our calculations of knowing our average amperage, our total seconds, Faraday's constant, the ratio of electrons to the copper, and of course the atomic mass of copper, the equivalent that Faraday found, all right, or at least the equivalent that Faraday was looking at and saw was based upon mole concept. We were able to calculate theoretical grams, and of course we ran a percent error. Okay, our percent error could be positive or negative. Do not take the absolute value. I want to know where you were in this lab. So now we're writing a conclusion. Conclusions have 2 parts for me. The first one is, hey, tell me what you found. Half of my conclusion is, what did you find based on our objectives? Our objectives were, of course, to determine the experimental mass of copper deposited at the cathode. All right, that was, of course, the first objective. The second one, and probably the most important one, was to determine the accuracy of our results, because that's where we want to spend our time on, of course, the error discussion. We want to embrace error, because understanding the errors, the limitation in this lab, is really understanding the process. So, where are the errors here? First half of our conclusion, we're going to tell me what we had, or what we achieved in lab experimentally. Percent error, experimental mass of the copper, boom, you have 5 out of 10 points for me. The next half of the lab, or the conclusion, is error analysis. Do not just write and list the errors. I need you guys to explain in detail, based upon logic, what you think, okay? You can't be wrong here, but you can be if you do not support what you think is limiting your experimental value. But this has to be based upon what the value of percent error is. If it's positive, remember, it's measured minus theoretical. So if your value is positive, you're above what we expect. Why did we get a value that was above what we expect? If your percent error is negative, that means that your value in lab, your experimental, is less than what we expect. And I want to know why. But again, could be competing errors going on that got you to be above or below. I want that discussion in detail, and I'm going to grade it as such. So let's go over some possible errors. First of all, we know that our entire calculation is based upon the amperage being at an average of 1. That is certainly a limiting part of this experiment, okay, because we couldn't set, based upon the devices I gave you, an amperage to stay at 1. it probably meandered a little bit, especially if you weren't watching, it went up on you. But I know that people did try to keep it at 1, but we know that that was certainly limiting. If we know the amperage is a little higher, then we know that you produced more coulombs. Remember, amperage is nothing more than coulombs per second. So remember, the whole point of this lab is to see how much charge in coulombs the electrons deliver is being pumped through this wire. So being above or below that average obviously brings your measured value above or below the theoretical. And that's something to discuss for sure. Okay, what other errors are inherent in here? Well, first and foremost, we know that we're dealing with an aqueous solution. That means the most predominant chemical species in this beaker is water. And what do we know when we send a charge or a voltage through water? Well, we know that we're going to oxidize and reduce water. So I expect a discussion about what's happening at these electrodes in terms of specifically where is water getting oxidized, where is it getting reduced? Obviously at the cathode, water is getting reduced, red cat. And what's being made at this cathode, okay? And you think about that, if we're doing electrolysis of water at the same time we're doing electrolysis of copper chloride, can you think possibly what may be limiting this lab? Well, to think about it, if I'm taking and assuming that all of the coulombs of charge that are being pumped by the battery through this electrolytic cell, we were assuming theoretically that all these coulombs were being used, okay, that charge of electrons. Remember, the coulombs give us a way to measure how many electrons are being used at the cathode by the copper. Well, think with me. If there's water getting reduced, then some of that charge, amperage, electrons, are being used by the water to get reduced. I expect a discussion about both places. All right. So think of how that might increase or decrease your experimental value as compared to the theoretical. Remember, the theoretical, the pencil and paper work that you did to calculate how many grams is based upon absolutely no errors. All right. So that's really important discussion there. Also, think about these conductors. These conductors are not superconductors. Superconductors are conductors that don't lose any energy when they conduct charge. All right. If you remember, and you think about this, was your beaker hot or cold after this electrolysis? And if you remember, we did a hot filtration. We didn't have to heat it because the beaker was warm. Why was it warm? Well, pushing charge around these wires into this conductor gave off heat, gave off energy. That means that some of the energy is being converted to heat. And we know that conductors aren't superconductors unless they're in a set of conditions that are hard to get, obviously, in lab. We'll talk about that another day. So a conductor like the copper or even the graphite here isn't perfect, which means that all of the electrons, okay, that we're trying to conduct, they don't quite get here, okay? And there's a reason for that, and we know that to be true when we're taking and pushing electricity over long distances. It's a voltage drop, and voltage drop and amperage drops accordingly. Okay, you notice when we pumped up the voltage, the amperage drop increased or decreased. So as we pump power or electrons through, and again, energy and electrons are different. Voltage is the force to push the charge, and amperage is the amount of electrons, but we do know that there's going to be a loss of energy as we try, it's called a voltage drop, as we try to push electrons through a conducting wire. So what we may read here may not be what's happening here, okay? Obviously, graphite and these wires are going to use some of that energy. So we would expect that error, of course, to lower, okay, the amount of coulombs as well, all right? Because obviously we're not getting those electrons all the way here, although we may read that, because some of that electrons are lost through the conductor and of course changed and converted to heat. All right, so what else do we have? Okay, well, those are some ones to think about, but also we have the copper itself. If I was to bring up a piece of copper, okay, into this discussion. All right, let's bring up some copper. This is an example of one of the students collected copper, okay? Now, before we collect and talk about the copper collected, how did we collect the copper? We shook off the mossy copper that collected, and then we poured it into our filter paper. And as we always talk about, as careful as we might be, did we get all of the copper that was made onto the filter paper in the funnel? And as much as we would try and run this over, we're always going to miss some. It's very difficult to get every piece of precipitate, or in this case solid copper, all right? And we can call it a precipitate because it came out of the solution, all right? Although it's not a precipitate in the sense of an insoluble salt, it's a solid, and it doesn't dissolve because of its zero, but it's hard to transfer all that, solid there, all right? Now, inherent in the lab, we collected all the copper on the filter paper, and then we put it in the oven, and we dried it. And then I give it back to you to measure, all right? And I did this purposely to think about, is there an error in this process of me giving you back filter paper, okay, and saying it's dried? Remember, it's wet. We had a solution, okay? We don't want to measure the water. But I gave you filter paper saying it was dried, yet we never verified it was dried. Think about a procedure experimentally that I could do to make sure that this filter paper is dried, okay? I didn't do it in this lab, all right? And for time reasons, but think about how that may have limited your results. If you had a positive percent error, which means that your measured value is way above what you expect, you could say possibly there was more amperage going on. We didn't control for that. But we know there's a lot of negative errors here. There's a lot of errors that are taking these amperages away. Being way above may be due to that filter paper having still some water in it. Couldn't I have taken this out of the oven, massed it out on a scale, put it back in the oven, and bring it back and see if those values decrease? I can keep doing this until the mass of my filter paper and my copper stay constant to verify all the water has been evaporated off. We didn't control for that, okay? So there could be an error there, all right? And last and not least, let's look at the compound that we collected here, okay? I'm just gonna put it up here. And again, colors are hard for me to see, but this copper was under high heat in an oven. And although not the easiest to see, we can suspect that some of that copper, okay, reacted with the oxygen to make copper 2 oxide. We can expect that there was some rusting going on. There was some oxidation, especially under high heat. So our pure copper, okay, definitely is going to react with the oxygen. That's why if you notice some of your copper might have a green a patina to it, a green rust color to it, okay? So so what's happening there? So if I've got pure copper, okay, atoms, and there was oxygen that was pulling electrons, and oxygen, if you look at your standard reduction potential tables, oxygen is strong enough to yank electrons from the copper. We're going to make a copper oxide. And if I make a copper oxide, aren't I going to have oxygen ions that are going to be added to my copper? Absolutely. Okay, a rust or the ore or the salt form of the metal, this being positive because it lost, and this being negative because it gained, would be my, of course, ionic compound that would coat the outside, all right? And of course, really what that means is you're adding oxygens, okay, atoms or ions in this case, onto the copper, and you'd be adding weight to your experiment, which would of course make your experimental value should be greater than what's expected. So a lot of competing errors here to think about, but I want you to use all of them and make a discussion about where your experimental value is to try to explain it. Remember, just because an error is negative doesn't mean you can't discuss it, meaning if your error is driving your experimental value below the theoretical, it doesn't mean that I can't talk about a positive error that got me even closer, right? So if I think that my theoretical value is here, and I know it's here, and I know that I have a negative percent error, I can still talk about all the things that have limited my result in that case, but I can also talk about the fact that maybe there were some other errors that even closed some positive errors that got me closer. All conjecture, use your logic, explain it using your understanding of chemistry, and if you support it with good explanations, it's correct. So I hope that helps in understanding the limitations of the lab and the lab in general.